Okay, for those of you watching the recording, I just barely started. And for the first couple moments, I forgot to hit record. So right now we're working on Newton's method. And we'll be using this formula right here. And then set the function equal to 0. And then I called that the f of x function. Now we're on to what's the derivative. So the derivative of sine, that's cosine. And the derivative of the e function is the e function. But then you need to do the chain rule and take the derivative of the negative 2x. So that means multiply by a negative 2. So that means that the general formula is going to be take x and then the function, so that's sine of x minus e to the negative 2x divided by its derivative. So that's going to just be cosine of x. And then a negative and a negative will make it positive 2e to the negative 2x. So does anybody have any questions so far? Okay, sounds like no. So the next thing is I need a first guess. And of course I could use a graphing calculator, but back in the 1600s when Newton was doing this, they didn't have a TI-84. So let's see if we could do it without a graphing calculator, at least for this first part. So this original problem says, when does the sine function, so the sine function goes like this. When does that equal the e to the negative 2x function? Well, if it was just the e function, it would look like this and it would grow exponentially. But because it's a negative exponent, that's going to make it go down like this. And then my question was, find the smallest positive solution. So they might intersect for a second time over here, but it looks like the smallest solution would be right here. And I know that this is pi over 2 when sine gets to be equal to 1. So pi over 2 is a 1.57. So I would guess that this is something like, I don't know, a 0.8. So I'm going to use 0.8 as my first guess. Okay, so we would then, you actually are supposed to write down my zero guess. In other words, I've plugged this into Newton's formula 0 times, and I'm guessing that it's a 0.8. Then take that 0.8 and plug it in for x in all of these places. So that's going to be a 0.8 minus, and then sine of a 0.8 minus e to the negative 2 times a 0.8, and then cosine of a 0.8 plus 2e to the negative 2 times a 0.8. And of course, we do have calculators, so I'll put this in the calculator. But that's a lot for me to memorize, so let me just write it down real quick. Let's see, the calculator should also be in radians, which it is. Okay, that sounds good. And then I always like to have my calculator on 3 decimals, but I was explaining something to someone yesterday. I put it on 1, so now it's in 3 decimals, 0.000, yeah. Okay. Now we're gonna need to type this in several times, and I really don't want to have to type this into the calculator several times, so I'm going to do it just once. So here's where the calculator turns out to be especially helpful on this. So first of all, I'm going to take the 0.8 And then on the bottom left-hand corner, it says STO with an arrow. So that means store that. And then store that as X. So now anytime I use an X, the calculator says, oh, you mean 0.8? Perfect. Then I'm going to type the formula, and I'm actually going to type it like this with the X's. And then since I stored X in its brain, the calculator is then going to substitute 0.8 for all of those X's. So then it goes X minus, and then the numerator had sine of X minus the E function to the negative 2x. And then I need to put parentheses around that, saying that's the numerator, divided by the denominator also needs parentheses, and it has a cosine of x, and then plus 2e to the negative 2x. And then that needs parentheses to say I'm done with the denominator. And now the calculator will plug in the 0.8 for x, and it says that your 0.8 was a pretty good guess, but actually it should have been closer to 0.332. So I'll just write down that is my second result. Now by doing this on the calculator, I can save a lot of time, because now I can just say store that answer as x, and rather than having to type it in again, just go up and do a screen grab. And if you happen to have an older version of the calculator that doesn't let you screen grab, then all you have to do is put second, and in the bottom right-hand corner, enter. That'll be the last thing we did. I'm going to do it one more time. Second, enter. And so that was the formula, but now it's going to plug in the 0.332. Now it says 0.428. As soon as I get the same answer twice, that's when we're done. So store that as x, and then I'm just going to grab that. Oh, it's getting close because the 0.4 stayed the same, but now it's 434. Store that as x. Repeat the process one more time. And I got the same answer twice. So that means, at least as far as 3 decimal places, then we're done. That's the first positive solution, 0.434. Then I go back and so I would have x0 was a 0.8. And then the first time I did the Newton's formula, I got a 0.332. The second time I got 0.428. The third time and the fourth time, they were both the same. That was 0.434. And then as soon as those two are the same, we're done. So do you have any questions? Yareli, Daisy?
So like once we have our like initial like our guess, then from there like our answer we can just like re-plug it into the equation.
Yes. Yes.
Okay. Just making sure.
Now, there would be times like if you said, oh, I think the answer is going to be 5. Well, that is not even close to the 0.434, which means that you would have to do the formula. Like I did it, what, 4 times? So I had to do it 4 times until I got the answer. But if your first guess was really bad, then it might take longer. But most of the time, it works.
Okay. As long as you have like a good guess, right?
Right. There's actually only one time when I've seen that Newton's method doesn't work, and that was actually at a math teacher's conference where the guy made up a function. so that it wouldn't work. But that was his whole point, is he was trying to show I can make up this function that Newton's method won't work on, but otherwise it works.
Okay.
So I just want to go and check and see if I got it right. So I'm going to go and grab the original problem real fast. So when does sine x equal e to the negative 2x? So when does sine x equal e to the negative 2x? And my numbers are way too big. I was looking at something else yesterday. Oh yeah, this is way too big. So go from like 0 to 2 on the x-axis. And then, let's see, the biggest sine gets is 1 and -1. So -1 to 1. And then there's this, which my graphing calculator tells me that x should equal 0.434. All right, then on to the other one, or number 2 anyway. So where's the function concave up? So that means we need the second derivative to be positive. And I actually did one like this last week. And the reason that I'm doing it again is because, well, part of with these AEWs, I do new stuff, but then also things that I know give people trouble, then I might work 1 or 2 of those in. And then also, I wanted to show you that, for example, on this one, if you need to do the second derivative, it's going to be a decent amount of work. Because for the first derivative, you'd have to use the product rule. So the derivative of sine is cosine. And then that cosine, that second cosine will stay there. Then the product rule goes plus. Now leave the sine alone and take the derivative of the cosine, which is negative sine. And that's the first derivative. Now, when you do the second derivative, you'd have to use the product rule here and the product rule here, and it's going to be even twice as long as this. And then we would still need to set it equal to 0. So part of the reason that I made this one up is you could use a trig identity. So there's a trig identity that says sine of 2x is equal to 2 times sine of x times cosine of x. Well, this is what the original problem says, sine times cosine, but it's just missing a 2. So with this original problem, what I could do is multiply both sides by 2. And by multiplying by 2, you do not change the concavity, whether it's concave up or concave down. And then on the right side, that's the trig identity for sine of 2x. Now we could take the derivative, and it's going to be a lot less work after using this trig identity. On the left side, the 2 would just sit there. You take the derivative of y, so that's y prime. Then the derivative of sine is cosine of 2x. And then by the chain rule, take the derivative of 2x, so that's a 2. Oh, and I could even at this point simplify it, because I could divide both sides by 2, and then it would just say y prime equals cosine of 2x. Which that already is simpler than when I did the product rule a minute ago and found the first derivative. So now for the second derivative, the derivative of cosine is going to be negative sine of 2x. And then by the chain rule, take the derivative of 2x, and that's a 2. And I want to know where it is the second derivative is positive. Well, the number that separates positives and negatives, that's the number 0. So if you set it equal to 0, That's going to be where it's separating between where it's concave up and concave down. Or in other words, that's where we find the inflection points. So I'm just going to put the 2 in front. So you could then divide both sides by -2, and that's going to leave 0 equals sine of 2x. So when does sine equal 0? So for the moment, I'm just going to ignore the 2x, and basically it's saying, when does the sine graph equal a 0? So the sine graph goes like this. This would be 2 pi. This would be pi. This would be 0. And, oh yeah, I said on the interval from 0 to 2 pi. So I'm actually, because of this 2x, I'm actually going to have 2 cycles of cosine. So this would be 4 pi, and this would be 3 pi. Now that's just for the sine function. Now I need to pay attention to the 2x. So when does 2x equal 0, or pi, or 2 pi, or 3 pi, or 4 pi? So it would be 2x, when does that equal 0? 2x, when does it equal pi? 2x equal to 2 pi. 2x equal to 3 pi, and 2x equal to 4 pi. And then to solve for x, all I need to do is divide them all by 2. So it's going to be x equals 0, x equals pi over 2. Then this one is going to be divide by 2, so that's going to be pi. The next one will be 3 pi divided by 2. And the ultimate one, divide 4 pi by 2, so it's 2 pi. And then what I like to do is put them like on a number line, or at least just put them in order. So let's say this is 0, this is 2 pi, in the middle would be pi, right here's pi over 2, and right here's 3 pi over 2. Then there's two ways that you could do this. You could then pick a number, like for example, the number 1 would be right here. And then you plug that in here to find out, is the second derivative positive or negative? So if I plug in a 1 for this x right here, that's going to say negative sine of 2 times 2. So negative sine of 2 times 2. So it's a negative 1819. The actual number doesn't matter. I just needed to see if it's positive or negative. And this is negative. So that means that on this whole interval in here, the second derivative will be negative. Now, you could keep doing it that way. You could also graph the original function and see where it's concave up. So I'm going to graph the original before I did anything to it. So that's just y equals sine times cosine. So y equals, oh, that was silly. I just erased sine of x and now I'm putting it again. That's okay. It doesn't cost me that much work. So sine times cosine, and the direction said go from 0 to 2 pi, and negative 1 to 1. I think I should be able to see the graph. All right, there we go. So pi over 2 was, so 0 to pi over 2 was one of the intervals. So then let me type in pi divided by 2, enter. So at that point right there, that's where it's changing concavity. Back to the worksheet, and each and every time I make these up, I give myself more space and more space and more space, and yet I still don't have enough space. Okay, so one way to do it is with the number line like I was doing. And when I plugged in the 1, I got a negative. So all of this is concave down. And if you look at the graph, yep, that part looks concave down. And then this part is going to be concave up. So that corresponds to this part between pi over 2 and pi. So this is going to be concave up. And then the next part, that's concave down. So that's, this part is this part is concave down. And then it switches back to being concave up. So that's this part, concave up. All right, finally, I just need to write down the answer. So the final answer is, so my question was, where is it concave up? So now I just need to write those intervals. So I think make it black so it stands out. So concave up. So that would be this interval. So that's between pi over 2 and pi. And then make sure you use the round parentheses, because those points aren't included, because right there we found out the derivative actually equals 0. So it's not positive at pi over 2, it's 0. And the same thing happens at pi and 3 pi over 2 and 2 pi and 0. Okay, so then there's also this interval. So union from 3 pi over 2 to 2 pi. And those are the intervals where it's concave up. Well, any questions on that one? All right. Next one that I made up was prove that this function is never concave down. So concave down means the second derivative is negative. And then show that that will have no solution. There's no way that the second derivative could be negative. Well, first things first, take the first derivative. So the derivative of natural log of x is equal to 1 over x. So whatever this thing is in the argument, you put 1 over that. So for us, it's going to be 1 over x. So the derivative of natural log is 1 divided by what's in the parentheses. So that's going to be 1 over x. And then the chain rule says now you need to take the derivative of 1 over x. And that's one that we use so often. I say you should just remember it. The derivative of 1 over x is negative 1 over x squared. Okay, then simplify this. Well, for this part right here, if you have 1 divided by a fraction, that means invert the fraction. So that's going to become, instead of 1 over x, it's going to become x over 1. Then just recopy this other part for a moment. And next, this x is going to cancel one of these x's. So once I simplify the first derivative, that's going to be negative just 1 over x. So there's the first derivative, and now for the second derivative. Well, like I said, the derivative of 1 over x is negative 1 over x squared. So the second derivative here, well, the negative sign that was already there, it stays there. And then for the derivative of 1 over x, that'll be negative 1 over x squared. And then those two negatives will cancel, which means that the final answer for the second derivative is just 1 over x squared. So prove that it's never concave down, or in other words, that the second derivative is never negative. Well, the number 1, so at this point, you could just explain it like this rather than doing mathematical equations. The number 1 is positive. When you square something, it's always positive. And then a positive divided by a positive is positive. So that means that this double derivative is always positive. So even if you put a negative 7 in there, so because it says x squared, negative 7 would be a positive 49. So 1 divided by positive 49 is positive. The only exception is you can't divide by 0. Except if you plug in a 0, it's undefined. And undefined is not negative. So therefore, I showed that there's no solutions that'll make it negative. Okay, then, have you guys done antiderivatives? I know in my class we're doing it later this week. Daisy, have you done antiderivatives?
No, not yet. We just started learning the L'Hopital's rule.
Oh, yeah, we're going to do that in number 7. So maybe, well, that's all right. I'm going to do it anyway. Okay, so if you have something like y equals x cubed, then you could take the derivative by using the power rule, which means that you take the 3, you bring it in front and multiply, and then you subtract 1 from the exponent. So that means that the derivative is going to be 3x squared. Now, antiderivative means go backwards. Oh, that was an ugly arrow. There we go. Antiderivative means go backwards. If you know what the derivative is, then go backwards and find out what the function was. So that means that for the power rule, we would have to do the opposite. So instead of multiplying by 3, we would have to divide by 3. And instead of subtracting 1 from the exponent, we'd have to add 1 from the exponent. And you have to do those steps in the opposite order. So it starts with the exponent. So instead of subtracting 1, you do the opposite, you add 1. And then that would make an exponent of 3. Then divide by that number. So then going backwards, it would then tell us that y equals, so the 3's would cancel, and then the exponent would be 2 plus 1, so it would be x cubed. And sure enough, if you take the derivative of x cubed, that's 3x squared. So then that's working backwards. So this is called a couple of things. Find the antiderivative. So anti is saying the opposite of the derivative. And then because saying find the antiderivative takes a long time, you could replace all that with the word integrate. Now, actually, integrate means to put pieces together. So take different pieces and put them together. And I don't know if we could do it next week or the week after, but there's a very good reason that the word integrate is used in place of the antiderivative. And then to say the word integrate, that takes a long time because you got to go to integrate. And then when you write it, you got to think, is it spelled into great? Like it's a great idea? No, it's not spelled that way. So then to replace all of that, we could just use a symbol. And the symbol is basically an S. So if you take an S, but then you stretch it, oh, that's just zooming. Anyway, if you stretch it to make it taller, that's what this is. It's basically just a tall S. And so then you would put the function, whatever it is, you'd put it right here. And then right here you put dx, which means that you're saying the variable is x. So if I said find the antiderivative or integrate 3x squared, so that's the same as going backwards. And then I would get the answer x cubed. So is this too much new stuff?
It makes sense. I understand it now. Like instead of the words, like there's symbols to make it easier. So I think like once you explained it, it made more sense.
Oh, good. Yeah. Now, before we go on to do those examples that I made up, there's one other small detail. And that is, if you check my answer, so here was my answer, or here was my answer, and you take the derivative of my answer, you will get y prime equals 3x squared. So it seems like I did it right. Nothing else to talk about. But what if somebody said, you know what, I got a different answer because I got plus 17. And I'm like, what? Where'd you get 17? And they're like, I just like it. It's my favorite number. But check it out. Does it work? So take the derivative. So it's going to be 3x squared. And then the derivative of 17 is 0. So it's gone. So in other words, whoever said the plus 17, they were right. That is possible. And then somebody else says, well, my favorite number is 42. I want you to put a 42 there. And then somebody else says, no, my favorite number is a 7. And then somebody else says, oh. So what we do is we just put the letter C, and then that stands for a constant. And whoever wants to put a 17 could put a 17.
Okay.
And so basically when you do the integration or you do the antiderivatives, then you'll always have a plus C. And one last detail. There are going to be times like on number 8 here, when I give numbers to plug in. And so these numbers right here, it's saying x is equal to a 0 and y is equal to a 2. And those numbers are there so that you could actually solve for C.
Okay.
Okay, so now with number 4. Well, number 4 is a quotient, and we can't use the quotient rule because that's for taking derivatives. And basically, the only rule that we have at this point is the antiderivative of x to the n with respect to x. So you would do the opposite. You would add 1 to the exponent, and then you would divide by that number. And then somebody's going to say, wait, do my plus 17. And then I say, okay, I'll call it c. So there's the plus the constant. So since that's the only rule that we have so far, we basically need to make the function look like something to the n. So not a fraction, I mean, not a one big fraction, but just x to the n. And the way that I could do that is by using algebra. And on number 4, this can basically be, instead of one big problem, you can divide it into 3 small problems. As long as you keep the denominator the same. So in pre-algebra, we teach people things like this: 2/7 plus 3/7. The denominator is the same, so you can add them and you keep the denominator the same. And then you add the 2 plus the 3, so the answer is going to be 5/7. And most of the time, we go this direction from left to right. But because that's an equal sign, that means you could go this direction and you could take one fraction and divide it into 2 fractions as long as you keep the denominator the same. So that's what I'm doing on number 4. So the first one, it's going to be x squared over x squared. The second one is 7x over x squared. And the third one is 3 over x squared. And then I just put the dx to say that x is the variable. And then I could even simplify the first one, x squared divided by x squared, that's just a 1. And for the middle one, you could say that it's 7 over x. Or you could rewrite that as 7 and x to a -1. And usually I don't like to work with negative exponents, but because the rule of integration says it should be in the form where it's x raised to a number, that's what we need to do. So this middle one is going to be 7 and then x to a -1. And then the next one, I could rewrite it as 3 and x to the -2. Okay, so then find the antiderivative. So with this number 1 right here, it doesn't even have an x. And yet I'm supposed to be using the rule that x to the n, its antiderivative is going to be x to the n plus 1 over n plus 1 and then plus a c. Well, with this 1, I could replace it. I could replace it with x to the 0. Because x to the 0 is equal to 1. And then I could use this fancy rule over here for finding the antiderivative. So you add 1, and 0 plus 1 equals 1, so then divide by 1. So that means it's going to be x to the 1 divided by 1, so it's just x to the 1. And at this point, I'm done integrating, so I don't write this symbol anymore. We're done with it. Now something interesting is going to happen for the middle one. So use the same rule. Add 1 to the exponent and then divide by that number. But now the exponent is a -1 and a +1, that makes 0. So then divide by 0. That is bad news. Dividing by 0, that's not good. So I have to think of another way to do it. And this happens with finding antiderivatives. There's not just one rule. In fact, when you take second semester calculus, so in Math 3A, we do a little bit of antiderivatives. Well, we do a decent amount. But in Math 3B, there's like a whole chapter dedicated to just finding antiderivatives. And sometimes you got to be creative. So I'm going to go back to when it was this one. And another way to write that is you could have one of the x's or the x on top cancel one of the x's. So that means it's 7 over x. Now this over here is one way to find antiderivatives. Another way to find antiderivatives is by using the derivatives that you already know. So for example, if it said the derivative equals -1 over x squared, then what did I take the derivative of? In other words, go backwards. What did I take the derivative of to get that? Oh, okay, it would be 1 over x. And the one that I actually need to use is this one right here, because my function is 7 over x. Well, the over x part, that came from somebody took the derivative of natural log. Go back to this. So basically this is 7 times 1 over x. And if you go backwards, what did somebody take the derivative of to get the derivative equal to 1 over x? So that's natural log of x. And the 7 could just stay there. All right, there's the antiderivative of that one. And then for the last one, we could use this rule over here because it's not going to cause division by 0. So just add 1. And then its exponent is going to be a -1, so divide by -1. So that means it's going to be a -3, so -3, and then x, and x exponent is going to be a -1, and then there's the constant that goes at the end. And then the only thing I would do for the final answer is x to the 1 just equals x. And then for this last one, instead of leaving the -1 exponent, I would just rewrite it as 3 over x. Okay, so that was a quick introduction to antiderivatives. And I think that I don't really have time to do number 5 and number 6. Maybe we'll save those and do them next week, because we should do some L'Hopital's rule. So finding limits, if when you first look at it, it is 0 divided by 0, or it's infinity divided by infinity, then you could use L'Hopital's rule. And whenever I spell it in my head, I say the word hospitals. But being French, it's a silent H, a silent S, because obviously H's and S's in the middle of a word should be silent in French. Anyway, with this one, its x is going to 0. And sine of 0 is equal to 0, even if you square it. And sine of 2 times 0, oops, that's not 20, but 2 times 0. That means this one is 0 over 0. So that means that we are allowed to use L'Hopital's rule. And L'Hopital's rule makes things much easier. So in my class, I ask people to put either write out the word L'Hopital's or just abbreviation like this so I know what they're doing. And L'Hopital's rule goes, look at the top and take its derivative. So the exponent of 2, you have to bring it in front and then subtract 1 from the exponent. So that's going to be 2 times sine of x. And then inside of that square function is the sine function. So I need to take the derivative of sine, which is cosine of x. And for the derivative of the bottom, the derivative of sine 2x is cosine 2x. And then because of the chain rule, take the derivative of 2x is a 2. So then let's see if we could just plug in 0. So if you plug in 0, because x is going to 0, if you plug in 0, is it going to be defined? If so, we're done. So let's see, this would be 2 sine of 0, cosine of 0, cosine, and then 2 times 0, that'll be 0, then times 2. So sine of 0 is 0, and cosine of 0 is 1. And on the bottom, cosine of 0 is 1 times 2. So that means on the bottom, it's a 2. Since there's no division by 0, that means it's defined. And on the top, there's 2 times 0 times 1. So it's 0 divided by 2. The answer is 0. So I want to see if I got that one right by looking at the graph. So graph this original function right here, and then see what happens when x is close to 0. So it's sine squared divided by sine of 2x. Y equals sine squared divided by sine of 2x. And then if you look at where x is equal to 0, sure enough, it looks like the y value is equal to 0. Now, if I move exactly on that point, it should say undefined. But as long as you're close to that point, then the y value is very close to 0. So I believe I got that one right. Next up, well, since x is going to infinity, e to the infinity is infinity, and 2 to the infinity is infinity. So that means that we are allowed to use L'Hopital's rule. So it's still going to say the limit as x goes to infinity, and then on the top, take the derivative of e to the x. That is the easiest derivative there is. Derivative of e to the x is e to the x. And then for the derivative of 2 to the x, let's see, where is that? Oh, here it is. So this would be the 2 to the x. So it would be 2 to the x, and then the natural log of 2. So that would be 2 to the x, and then times the natural log of 2. And if you look at the original problem, notice that it's basically still there. The only thing that changed is it's times the natural log of 2. And if x is going to infinity, that means that the top is going to infinity and the bottom is going to infinity. So that means you could do L'Hopital's rule again, which sometimes is helpful and sometimes is not. And with this one, it's not, because the derivative of e to the x is still e to the x. And the derivative of 2 to the x is still 2 to the x times natural log of 2. So the problem is not getting any simpler. It still has this, which is the core original question. All it's doing is adding on some natural logs of 2. But the core problem is not really being solved. What else could we do? Okay, L'Hopital's rule is fun, but it can't solve everything. So we have to think of another way to do this. Well, then I noticed that this one is raised to the x and this one is raised to the x. So what I could do is say, since they're both raised to the x, I could just say the whole thing is raised to the x. And then it's the number e divided by the number 2. So basically just pull that exponent out and put it outside the parentheses. So then what is e divided by 2? Because e is a number, 2.718. So how much is e? And the calculator is going to make me put an exponent of 1. How much is e divided by 2? It's a 1.359. So if you put your money in the bank into a savings account, and then your bank was very generous and they said, you know what, we're going to pay you 35.9% interest. My bank actually pays me 0.02% interest. That's Bank of America. But maybe you have a better account, so you get paid 35.9%. Then if you said, well, I'll put $100 into that account. Well, this formula right here is telling you how much money you would have, because the 1, so 100 times 1, that's basically just keeping your money there. And then the 100 times this decimal, that's paying you interest. So if you had $100 and you're getting 35.9% interest, and you left it there for a year, well, you would get $35.90 interest. So now you have $135.90 instead of $100. And if you then left that money there for 10 years, and by the way, if you ever do this, don't leave your money there for 10 years and not check on it. You have to check on it at least every 7 years. Because if you leave money in a bank account, not that many people do this, but if you leave money in a bank account for 7 years, the bank then turns it over to the state of California and says, this money has been abandoned. There's actually websites where you can look up and see if you or any of your relatives have money that's been abandoned. Anyway, so if you leave that money there for 10 years, instead of $100, you'd have $2,148.79. And if you left that money there for 100 years, you would have, that's like in the trillions. That's even more. Anyway, my point is that this is an exponential function that is just going up and up and up. So it's going to infinity. Oh my gosh, it's only already 12 o'clock. So I don't have time to do those, but I wanted to do this one. I really want to do this one. So another way to say find antiderivatives, or another way to say integrate, is to say solve the differential equation. In other words, if you already know what the derivative is, then what is the function? So using the rule that I said earlier is one way to do it. Another way is you just look at the function, especially that square root of 1 minus x squared, because that sort of sounds familiar. And then you search your memory card. Is there anything in here that has the square root of 1 minus x squared? Yes, somebody took the derivative of sine inverse. Now, the function had a 12 right here, so I could just multiply both sides by 12. So working backwards, the original function must have been 12 times sine inverse of x. So the original function must have been 12 times sine inverse of x, and then plus the c. And so by knowing derivatives really well, like in my class, especially when we're in person, then I emphasize you should know these derivatives really well, because not only do you need to go forward and find the derivatives, but you need to go backwards to find antiderivatives. So there we're done, except this one also has this information, which is what you use to find out what c actually equals in this case. So as I said earlier, plug in x equals 0 and y equals 2, and then solve for the c. So if y equals 2 and x equals 0, then solve for c. So what's 12 times sine inverse of 0? That should equal 0, because sine inverse of 0 equals 0. 12 sine inverse of 0. Yep, that equals 0. So that means 2 equals 0 plus c. So the c is equal to 2. And then finally, just go back and put that right here. So my final answer is 12 sine inverse, and then plus a 2. And there is the final answer for number 8. Well, I was really ambitious, hoping that we we're going to get to these others, but I think I need to wait on those until we could do fancier antiderivatives. So that's it for this week. Let me turn off the record.